So Converters theme has 5 universities in it, listed there: Bristol, Imperial, Manchester, Nottingham and Strathclyde. And what I was going to do was, first of all, just introduce the research team, people who've done the work, tell you a little bit about the vision, objectives, how we're organised, and then run through the various activities and give you a little bit of an update on what's been done so far. Here are the people involved in the theme. I won't read everybody's name out. The large font people are the academic leaders at the institutions. I think they're all here. And then under them, we've got a RA, postdoctoral RA at each institution, and they're each supported with a PhD student. Not all the institutions have got PhD students in place at the moment, but there are 2 or 3 due to arrive and start this summer. So in terms of vision and objectives, then we thought when we were planning this, how do we focus our efforts? And we decided that there were 2 big areas that we thought we had the potential to make a significant contribution in. One was in very high voltage converters, grid scale converters working at hundreds of thousands of volts. And the second was in the area of compact converters. Compact doesn't necessarily mean low power, so these could be converters up to 100 kilowatts or whatever, particularly driven by demands from the transport sector, but also many other sectors are looking for increased power density. So we picked those 2 broad areas as our 2 areas of focus, and that sort of formed our vision for the centre there. Areas where we've got significant strength in the UK already in the academic community, and we also have a good industrial base and good opportunities for industrial interaction and exploitation of the activities. A little bit more on the detailed objectives under each of those. Then the high voltage converter work. These are systems that operate at voltages that far exceed the capability of any individual devices. So they end up being converter structures that are made up of many devices in series or highly modular arrangements. So the objectives there are looking to identify new architectures, new topologies of converter, which allow us to increase performance, achieve higher voltage, increase efficiency, improve fault ride-through, and so forth. We're looking to try and understand better the complexity in these systems. As you get a highly modular converter, then they could have hundreds of cells made up in the types of things Paul was showing you a few minutes ago. Understanding the flows of energy between the individual cells in a converter like that. Understanding its performance under fault conditions and how to optimize it is a key challenge. And the third objective under that area is the work Paul's been telling you about a few minutes ago, which was all to do with exploiting the redundancy and control of these systems to provide some benefits in terms of managing the health of the system. So identifying cells that are aging, looking tired, and implementing strategies to remove the stress from those towards other parts of the system. In the area of compact converters, then I think the big area that we're looking to exploit there is the emergence of new devices. So we heard about new silicon devices from Phil Morby earlier this morning, and then we're all aware of silicon carbide devices and gallium nitride devices that are starting to appear. So a key objective for us there is to understand how best to use these devices, how best to exploit their characteristics within a converter, what topologies do we need to do that. Second objective under that heading is to start to understand how we can exploit new manufacturing techniques, new assembly techniques that enable us to build a converter in a more compact way. And the third objective there is to I should have had these listed on there. looking at the topologies, the manufacturing techniques, and the third thing there is the techniques for designing these converters. So understanding the interrelationships between the stored energy, between the sizes of the filter components, the EMI, the efficiency and so forth, leading us to ways of optimizing the system for a certain requirement in terms of efficiency and power density and so forth. So those are the objectives under those headings, and those are underpinned by activities in the three cross-theme topics that you've heard about earlier. So we've organised ourselves into these 4 work packages. We've got a single work package which brings together all the topologies work, and then under that we've got work packages in the 3 cross-theme topic areas: structural and functional integration, design tools, and the operational management and control. So we organised ourselves like that to give us the best chance of exploiting synergies across the centre in these areas. So the idea is that the new topologies work is going to be transformed by the technologies work in work packages 2, 3 and 4 into applications, and our aspiration is to have demonstrators at the end of the project there demonstrating a highly compact converter and a high voltage converter. In a bit more detail in what's going on in those work packages, then under the topologies area, 2 areas of work looking at the high voltage converters, both being done at Strathclyde, one looking at DC to DC topologies, and the second looking at new forms of AC to DC topology. So the AC to DC topologies are fairly well advanced, and applications are being developed for those. The use of those in DC to DC converters is a little bit more complicated, because in the DC to DC converters we'd like to have a high frequency transformer, so not a grid frequency transformer, and the sorts of topologies that we would use there are not straightforward. So there's research to be done to understand what those topologies should be. The AC to DC topologies, we're interested in looking at hybrid topologies. So these are topologies where the individual cells are not necessarily all the same type, but you could have a mixture of cell types to give performance improvements. The lower 3 bullet points there are the areas of work for compact converters. We've got 3 areas of work there looking at 3 classes of converter: AC to DC converters, where we're looking at multi-level techniques, but for low voltage converters, so converters less than 1,000 volts, where the multi-level topologies give us the capability to improve waveform quality, reduce filter size, and so forth. We're looking at soft switching techniques for multi-kilowatt DC-DC converters. Again, these are low voltage converters, less than 1,000 volts. And at Nottingham, there's work on matrix converter concept, advanced forms of AC-AC conversion. The structural and functional integration work package is looking to identify bottlenecks in how we make power electronics at the moment, and looking to identify ways of overcoming those bottlenecks, so better ways of manufacturing and assembling converters. And that's largely a Nottingham activity. The design tools and optimization work package is very much focused on next generation devices, looking at forming trade-off models of converters that use those devices, and providing a design framework to enable us to trade off the performance of a converter in terms of its efficiency, reliability, size, and so forth, to explore the design space and identify optimum designs. And the operational management and control work package, this is something you've heard about from Paul already, and is to do with the high voltage converters, and particularly devising new forms or new ways of controlling these highly modular converters to provide performance benefits in terms of managing state of health and so forth. So running through what's been done so far and what we're doing in these areas. First of all, the high voltage converter work at Strathclyde. So this work so far is focused on DC to DC converters, and as a substantial survey of topologies has been done, a simulation study of alternative topologies has been written up, and work is ongoing, starting to look at some prototype testing of alternatives. Two main classes of topology have been looked at. First of all, single converters, which can operate at very, very high voltage using the MMC type converter. And then secondly, converters which are made up of many much lower voltage converters. So this is the MMC type concept, where you can recognize here one of the MMC type structures, where we have these individual switching modules and then many of them together there forming part of a leg, along with the bit of current limiting inductance. 3 legs for a 3-phase system, and then you can see they're driving a transformer here. Not necessarily a high frequency transformer, but it's not a grid frequency transformer, so might well be several hundred hertz. 250 hertz, I think, was used in some of the simulation work. Over on the secondary side, then a mirror image converter, and by arranging the phase shift of the voltages across the transformer, then power flow can be arranged in either direction. The normal operation of these converters is that the modules here are switched in sequence to synthesize a voltage at the leg output there that's a sort of staircase type waveform, and produces something that looks sinusoidal. The work that's been done here has been looking at this so-called quasi two-level operation, where the switching of these cells are moved much more closely together to create an output voltage that's described as quasi-square here. And these are the output waveforms. So we've got the 3 leg output waveforms, and you can see the individual cells are switched one after each other fairly rapidly to switch the voltage from 0 up to the positive of the DC input there, and then it's held constant for quite a long time and produces a quasi-square waveform, and we do have balanced quasi-square waveforms. The advantage of that is the size of the capacitor in the cells there is reduced, and the switching losses are still controlled, and the conduction losses are reduced. So that's an operating pattern that's been investigated in that work. The other area of work is, as I mentioned before, looking at these highly modular converter structures, where we have an array of converters at the input, an array at the output, and an array of transformers in the middle. This is a simple example where we've got a whole load of things in parallel at the input, a whole load of units in series at the output, and those are obviously unidirectional systems where power only goes towards the right. We could have an active bridge on the right-hand side there, produce bidirectional power flow. And the challenge, I think, with these systems is that these individual transformers have to be able to cope with the total voltage that we have on the DC side, because of the way it's organized. So this one here, which is obviously at the top end of the string on the right-hand side, is still paralleled at ground on the other side, so it sees the full voltage of the output. So the design of those transformers and achieving isolation is a key challenge there. So there's some work going on at Strathclyde looking at a It's a silicon carbide-based cell at 1,000 volts to 1.5 kV at 10 amp level, and that's being prototyped at the moment to start to understand the design and the performance of these individual modules. Moving on to the work on compact converters, then this is some of the work going on at Bristol, where I mentioned before they're looking at multi-level techniques, not particularly for high voltage, so the voltages are assumed to be less than 1,000 volts, but the use of multi-level enables improved waveform quality, reductions in the filtering requirements, reduced switching losses, and the reduced losses then enable smaller heat sinks and so forth. So there's a prototype here. This has been using some of the new superjunction MOSFETs. One of the problems with the superjunction MOSFETs is the body diode performance is not particularly good, and the capacitance is highly nonlinear as well, which can lead to quite serious switching loss problems. So there's been a lot of work at Bristol looking at switching aid networks to suppress the operation of the body diode and achieve very efficient performance. So there's a prototype there at the 3 kilowatt level and some waveforms from it with efficiencies there of over 99% being claimed. This is some more of the work at Bristol looking at a comparison of different multi-level techniques for something around the 5 kilowatt 380 volt AC type output, and you can see the efficiency here worked out just in terms of the semiconductor losses, plotted against switching frequency for a number of different types of circuits. You can see the 2-level circuit here gives the lowest efficiency at a given switching frequency, and we're getting higher efficiencies, lower losses for the multi-level topologies. The best efficiency is achieved by a so-called pi-type converter, a 4-level converter, which is this circuit here, which is being developed at Bristol, and there are 6 devices there in each leg. And there's some work going on here looking at the validation of that circuit. So there's a prototype being built, and you can see the 4-level leg voltage, and it gives us a 7-level line-to-line voltage at the output there. Moving on to some of the work that's going on at Manchester, then we've been looking at higher power DC to DC converters. This is something we built recently at the 60 kilowatt power level, looking at using silicon carbide devices. One of the things we find, yes, we can push the frequency up with silicon carbide devices, but we still end up being limited by switching losses. And at a 75 kilohertz operation there, we found that over half the losses in the devices were switching losses, leading us to think about the use of soft switching techniques to try to reduce some of those losses and enable further increases in frequency and reductions in the size of the magnetic components. So there's a circuit here we've been looking at to reduce the switching losses. So this is a 2-phase DC to DC converter. It's a step-up converter. You can see the 2 switching legs there. They're combined with an interface transformer and an input inductor, and the elements in red is the switching aid network, which is being used to resonate the voltages across the main devices down to 0 before they turn on, and we've got some results here showing the drain voltage of a device coming down to 0 before its current rises here, giving us a low loss turn on, and this red waveform here is the auxiliary current in the auxiliary circuit. So that's shown an improvement in overall efficiency of a converter, reducing switching losses by about 50% and reducing the DVDT as well. And the development of that is ongoing to simplify the circuit, look at integrating this additional inductor with the other magnetic components and optimize its performance. One of the things it's led us to do is to look at the detailed switching transients that go on with silicon carbide devices. They switch very much faster than silicon devices do, and different parasitic elements start to become dominant and become important to understand. So our PhD student, Rishad, has just been doing some modelling to understand what those are, and he's developed a fairly rapid model simulation to predict switching waveforms and to incorporate some of the key parasitic elements, and they turn out to be some mutual inductances between different parts of the circuit are some of the dominant effects in those circuits. So moving on to the structural and functional integration work package, this is work being done at Nottingham, and there's been a major activity to do a survey of manufacturing techniques and processes. So a number of companies have been visited to have a look at the way they're organised and their processes for manufacturing power electronics. And they've covered applications ranging from just a few watts, so little power supplies, up to huge drives. And the objective has been to try and look at bottlenecks and identify issues which limit the performance, the cost, the ability to miniaturize these things, and so forth. And across all the companies that have been visited, the same sort of conclusions and similarities have emerged. I think this slide's just summarizing what's been found in terms of the process as an organisation and how they're similar. The diagram here is just organised to show in green the highly automated parts of the assembly, and the yellow is just showing the labour-intensive parts of the process. The forming and inserting an assembly of through-hole components is a serious issue which limits what goes on in many companies, and then the final assembly, very often of odd-shaped components, quite large components, limits what happens there as well. The supply chain tends to be quite similar for everybody. A lot of components are generic components, and they're just bought in and assembled. And a significant number of other components are custom designed, so a company would custom design them, like wound components or whatever, have them outsourced, bring them in, and then assemble them. And this slide summarizes the problems, the bottlenecks that are limiting the ability to improve performance of the system, largely arising from these pre-manufactured discrete components, wound components, heat sinks or whatever, that are made outside and have to be brought in and integrated, which is a relatively manual process. These things end up being quite bulky. They tend to lead to higher volume of the overall unit, and it's a labour-intensive process which adds cost. And the other thing that was identified is the generic components have very small profit margin associated with them, which then limits the capacity for those industries to invest in R&D and innovate and so forth. So this all contributes to the bottleneck of trying to improve the performance of equipments in terms of size and weight and reliability and so forth. So the work now at Nottingham is starting to think about ways of improving the assembly of power electronics, and in particular is starting to look at new ways of forming connections between components. So the diagrams here are just trying to illustrate the problems associated with having screw terminals going, for example, from a module to a bus bar or from a bus bar to a capacitor or whatever. And you can see here the current paths close together in part of the planar structure, but as the current has to flow to discrete points, then the go and return currents move apart, and we're creating current loops there and adding inductance, stray inductance, which is going to limit switching performance and so forth. So the work is looking at new ways of forming interconnections in power electronic circuits, which eliminate that additional stray inductance and are going to be suitable for automated manufacture. So there's a blade connector concept here being thought about, where you can see a planar bus bar here and some sort of receptacle that can plug into, which might, for example, be interfaced as part of a capacitor assembly or whatever, to allow a planar assembly of the entire power electronic circuit. So that's being developed at the moment. So in the area of design tools and optimization, the work, as I mentioned earlier, was focusing very much around new semiconductor technologies, particularly silicon carbide devices, and understanding how we optimize circuits that use these components. So this is the work that's largely been done at Bristol and is assembling design trade-off models of the various components within a converter, the silicon carbide devices, so these are loss models of the devices, models of the heatsink, telling you about the size of the heatsink according to the airflow and the heat it's removing, models of the filter and so forth, and then putting all of these into an optimization process to explore the design space to identify minimum weight solutions or whatever the objective is. So these are some results from Bristol looking at the design of so this is I think a 5 kilowatt active rectifier, and it's been designed to meet an aerospace power quality requirement. So we've got the graphs here showing the overall weight of the EMI filter and the different parts of the EMI filter, the common mode and differential mode parts of the filter. And the reason it's got these steps in it is to do with the fact that the EMC spec that's being used here starts to bite, I think, at about 150 kilohertz. So as the switching frequency goes up, which is the thing that's plotted along the bottom here, then as the first harmonic of the switching frequency moves into the specification of the EMC limit, then that causes a jump in the plot. So the plot over here shows the overall volume of the converter, showing at very high frequencies the volume obviously gets bigger due to the increased losses and the need for a bigger heatsink and so forth. And those are some results just showing the sorts of power densities in terms of kilowatts per litre and kilowatts per kilogram that could be achieved based on the technology that's been assumed in the models there, either with natural convection or forced cooling of the heatsink. And you see the best that's reporting is a little bit less than 10 kilowatts per litre. These are with two-level circuits. So the graph I was showing earlier illustrating the reduced loss with some of the multi-level circuits are likely to deliver much improved power densities there, because the losses will be lower and that the heatsink will be low. This is some work going on at Manchester looking at the optimization of DC to DC converters. This work started relatively recently, and the models here aren't as well developed, so we haven't actually got a heatsink model in here yet. So this is the effort has really been looking at modelling the inductor and the power modules and the capacitors. This is a two-phase interleaved converter, and again looking at the weight of the components against switching frequency. We're identifying a minimum weight here at something over 130 kilohertz. So that is being developed further to include the heat sinks and to include the capability to look at different numbers of phases in the converter. So our last work package, operational management and control. A significant part of the work here is the work Paul was telling you about, which was the way of condition monitoring the cells in a multi-level converter. I'm not going to tell you any more about that. What I've got here are a few slides to show you the experimental system that's being assembled at Imperial to provide a basis for validating some of the techniques Paul was talking about, and also for looking at some of the fault behavior of these systems as well. So this is a 15 kilowatt system. There are 10 switching modules in each stack, and it's got a DC voltage there of 1.5 kV. So there's some test results starting to come from this. This is the test bed that they've got at Imperial, where the converter under test is here. There's a grid link converter system, a back-to-back converter system to give a controllable AC voltage that's obviously isolated here for the AC side of the converter under test. This is the DC circuit here, where there's a capability for putting faults onto the DC link. And then there's another converter here which can take the power back to the grid. So power can be passed either way and provide a flexible way of testing the converter under test. And there's some lab pictures there. So there's some results here showing the thing working up at we've got about 10 amps peak, I think, here are the line currents, and up over 1,000 volts, I think, on the DC link. The individual cell voltages here are approximately about 70 volts each. And here's a result actually showing the thing being put into fault and recovering from a fault. So we've got the DC link voltage here in blue. There's a fault imposed on it. The converter that's being tested continues to provide current in a controlled manner into the fault, and then when the fault is removed, the system recovers the DC link voltage. So those results have just been achieved within the last few weeks as that system's been commissioned and put into use, and then there's going to be obviously much work going on over the coming 2 years using that rig to explore more further the fault behavior and the behavior with the condition monitoring techniques in the cells. So to finish with, just to say where we are, we've delivered so far. We've got 6 of our project deliverables have been completed so far. We've got 7 more due for delivery this year. So there are reports and papers on the various aspects of work I've been talking about there have been produced. We've generated 13 conference papers, 2 journal papers so far, and there are 3 journal papers under review at the moment. So that's the converters theme. Any questions?